Right, welcome back. So, by way of some theoretical explanation, of course, what we get is um, a typical kind of approach using pronumerals. So, in this case here, we've got the integral equal to e to the ax e to the ax plus b. I don't know where that score is coming from. And we do our usual process. And we'll find a general case and maybe an argument for a shortcut, but I have already said to you on many occasions, I am not a big fan of shortcuts, so I think they're flawed. But with experience, you can use them. So this will just become a. So we'll have 1 over a du equals dx, and this is the essence of u substitution for me. So we substitute that out for du. We'll get 1 over a, the integral of e to the u. This is now a much more simple arrangement, and so the integral of e to the u is simply e to the u. So we get, in the general case, 1 over a. So we can look for that plus c. All right, let's have a look at a few more u substitutions. Thinking about the derivatives and various explanations if we let, so this is a genuine u substitution, we'll call this now. So going through up and under quotients which were expressed as a u substitution, but I think I'll put that to bed. Now we can say squared. So du dx is equal to 2x, and after some multiplying and dividing, 1/2 du will be equal to dx. So we ask the question times x. Are you there? Yep. Are you there? Yep. So we get the x's left over. So they're both going to be substituted out simply by writing du. So we'll have 1/2 the integral, x is gone, the x is gone. So it's simply e to the u. So what's the integral of e to the u? The integral of e to the u is e to the u. So putting the u back in as x squared plus c. So we've managed to do that in a fairly straightforward way. All right, so we've got to look for these in terms of their derivatives. Is there a derivative? Tan x, sec squared x, possible? Okay, so what we're looking for is tan x sec squared x. So let's do tan, because we know the derivative of tan is sec squared. And not only that, this is a chain rule. So it wasn't good enough just to have tan x, we had to have tan 2x. So that means we've got to go away and work out du dx, staying in the column. So that means we can let, if u equals, let m equal 2x, then we can rewrite u as u is equal to tan of our new pronumeral m, and we can put our chain together. U dm and dm dx. Now they'll chain together to give us our du dx. There's our du dx. We just need to do them and put them together, and we'll have du dx. So dm dx is 2, okay, and the du dm is sec squared m. So putting the m back in, we end up chaining them together. Chain these together, we will get 2 sec squared m is 2x. So there's our dm dx. Now thinking about it, we've got a sec squared 2x, so we have that and a dx. So after a few lines of manipulation, we get 1/2 du is equal to sec squared 2x dx. Go away and ask our annoying question. Are you there? Yep. Are you there? Yep. They are both now subbed out. They're gone. And they're subbed out by putting in du half. Now this is what I believe is the best way to think about u substitutions. High school students can't come to me with that ready to go. The trivial substitution is now the e to the u. This is the trivial bit. Okay, but the integration of e to the u is e to the u. So we end up with 1/2 e to the u, which was tan 2x, plus c. So that's our solution. And of course you can check those on. Okay, so very happy for you to do that. Again, I think with the trig forms, I think it's just important to remember that ddx of sine is cos. So clearly if we integrate cos, we're going to go back to sine. Okay? The ddx of cos is minus sine, but we don't integrate minus sine, we integrate sine, so it's going to be the other one, minus cos. Anyway, I'll leave you to pick up how you do that, but either way, that's got to be done. Alright, so let's see if we can practice a couple of skills on it. So we've got our cos 3x. So it's again a substitution. Let u equal 3x. And u dx is equal to 3. So 1/3 du is equal to, after some work, dx. And that's the thing we're substituting out. And I think this gets lost big time coming out of school, substituting that. So we put our du in, that dx is gone. Don't forget your 1/3. And so we simply have cos u. Now the differential of sine is cos, so the integral of cos will be sine. So 1/3 sine u, and u itself was 3x plus c. That's our final. So stay in your column and finish your column, then do your substitutions. Alright, so let u equal 5x, u dx is equal to 5. So after some manipulation, we'll get 1/5 du is equal to dx. And so, are you there? Yep. So you're gone. You're gone by du and 1/5. So we'll integrate. Now, sec squared u is a simplified integration. So we end up with tan. Plus C, and that's our final capital C. That's our final answer. So these are not over the top difficult. It does take a little while to get used to them, but once you see the patterns coming out, it's a follow thing. Okay, it's very much a follow thing. All right, so we'll let the inside of the brackets be equal to u. The u, it doesn't matter which way you write them, the u dx be equal to 2x. So after a bit of transposing work, 1/2 du will be equal to x dx. Are you there? X dx? Well, dx is there, we can see it. X is there, we can see it. So you're gone. So x and dx are gone, and we substitute 1/2 du. And we're integrating the simple trivial solution. Sine. Okay, now the differential of sine is cos, so the integral of cos is sine. So the integral of sine is the other one, which is minus cos. So we get minus 1/2 cos u, which was x squared minus 1 plus c. That's our final answer. Very straightforward. So once you get the hang of the column, you get the hang of doing the thing, the pattern remains the same. All right, x dx cos e to the x, so we'll let u equal e to the x, du dx, differentiating u with respect to x, is equal to e to the x. Wow, that wasn't hard. Du is going to be equal to e to the x dx. Let's check it. Are you up there? Yes, I am. Are you up there? Yes, I am. So they're gone. They're gone by simply du. So that is an equivalent. The only thing we've got to put in is the trivial cos u. So we're integrating cos, so differential sine is cos, so the integral of cos is sine. U is e to the x plus c. Wow. Okay, plus c. So that's fairly straightforward, isn't it, I think? All right, let's have a look at the next one. Tan. Tan is rise over run. Remember that? Rise over run. Over run. Why am I doing that? Y over x. What's another name for y? Sine. Oh. Cos. So tan dx is an integral of sine over cos. X is the differential. We could do the u substitution. That would work fine. We could look. Actually, we'll do that. We'll do the u substitution. Now the differential of sine is cos, so we're going to take sine that u equal The differential cos is minus sign. How about we do that one? Cos, so du dx is equal to, differential of sine is cos, so the differential of cos is minus sine. So putting the dx and the minus down, so we get minus du after a few lines of working, equals sine x dx. Well, are you up there? Yep, there I am. What about you? Are you up there? Yep, I am. So you're both gone, and you're both gone by du. And don't forget the minus integral. And the trivial one now is cos. Cos was u, so it's 1 over u. Now most students coming from the HSC, I think, probably learn shortcuts, and when the questions change, it gets a bit tricky for them. So this is now, is the derivative of the denominator on the numerator? Yes. So it's of the form the log substitution. So just picking the right one. If you didn't pick the right one, try again. No, there's no worry about doing things again. All right, so if tan is y over x, what about cot? Well, it's the other one, isn't it? X over y, which is cos over sine. So this is now written as cos over sine. Does this one have this form? The answer is yes, the differential of sine is cos. So we don't even need to bother. We can go straight to the ln of the denominator. We could have done the whole rigmarole with the u substitution, but there's no need for it. Okay, from ln of c. Alright, so the final thing is we've got some tables there, we've got all of the regulars, so for these things where they're integrating sine or cos, see this one here, if I d dx sine, then I know that that's cos x. So that then, if we integrate that, we're going to get sine. So it's the reverse operation. Okay, so this becomes your antiderivative, and the differential of the antiderivative is in fact the function. Okay, so we've seen that earlier, so you can look that up. All right, that'll do for now. I'll catch you later.